Hi everybody, welcome back. So today we're going to talk about robust standard errors. It's pretty important that you understand what robust standard errors are, also called heteroscedasticity consistent standard errors. It's important because so many people use them. It's also important because so many people abuse them, use them the wrong way, are misled by them. And I don't want you to be misled by them when you use them in your research, if you do. And I don't want you to be misled when you read applications of them. And ideally, we'd like you to be able to correct your colleagues or others who come to you for methodological advice, wielding their robust standard errors, thinking that they have something that they actually don't. There are really valuable uses of robust standard errors. They will be useful to us in detecting problems with models, but they're not appropriate to be interpreted in the way that they often are in the literature. I'll explain all of this. This set of slides is based upon some research that Molly Roberts and I did. Molly was a student in this class and a teaching fellow, and she's now a professor at UCSD. So robust standard errors. Let's get going. As I said, they're widely used and widely abused. A few years ago, when we did this research, we calculated there were over 141,000 articles that used them, growing by about 1,000 a month. Robust standard errors are a way to estimate the variance of theta hat, the thing that comes out of after you find the maximum likelihood estimates. We want to find the variance covariance matrix of them. This is a way to estimate the variance with fewer assumptions than we usually do by the negative of the matrix of second derivatives. So that's a really good thing. But they're not a way to estimate the variance with no assumptions, and that seems to be how they're described sometimes. They're useful only when some assumptions are violated, not when all assumptions are violated, and we have to know which is which. They are not appropriate to use in the way that they are usually used, which is as a way to inoculate yourself from criticism. They don't do that, okay? So the way people sometimes use them, or often use them, is they don't have any particular reason to run robust standard errors, but they ran their regular standard errors, and they're trying to prevent evil anonymous reviewers from ruining their day, and so they run robust standard errors, and they report in their article that they ran robust standard errors and thinking that's a great thing. It may be a great thing, but it's not always a great thing. When the classical standard errors and the robust standard errors differ, what does that mean? Well, in the best case, some quantities of interest in for example, beta in regression, are unbiased but inefficient. So that's interesting. That's useful. That may indicate that there's a way of improving them. It also indicates that other quantities of interest, such as features that involve the probability distribution, like the probability that, in this example, y is greater than 0.6, or the probability that one candidate is going to win, they're biased if the model's biased. In the worst case, misspecification is more widespread, and all quantities of interest are biased, and the variance covariance matrix is misestimated in a classical way and in the robust way. Robust standard errors, thus, are a pretty good test of at least some types of model misspecification. It's not exactly clear which type of misspecification, but if you can detect that there's a big difference between the robust standard errors and the classical standard errors, and you can find that there is, and there is in your data, then that's an indication that something's wrong with the model you specified, and that fact is really useful. You can use that to go and search for what the problem was and see if you can correct it and improve your model. If it turns out that the robust standard errors and the classical standard errors are about the same, then that's great. You can report that, and you can indicate that that it passed the test of model misspecification. So that's good. So let's do a review. Let's put ourselves in context so we can figure out what we're talking about. A way to do this is in linear regression, because we can do all the math and we can get much better intuition. So regression model variance specification. In the linear normal regression model, we have y is normally distributed, mean mu, variance sigma squared. The systematic component is mu is a linear function of the x's. We have an independence assumption across observations. That's our linear normal regression model. We can rewrite that in a different way, which is in a matrix formulation. So I have this written in a matrix formulation where under each variable, which is a matrix, I have the dimensions of the matrix. It's always good to do that if you are doing matrix algebra, because the inner components of the matrices like this, when we multiply x by beta, in order to do a matrix multiplication, the two matrices have to be conformable, which means that the k here and the k here have to be the same. So the outer, this is rows by columns. So the columns of the first one and the rows of the second one have to be the same, or else you can't matrix multiply them and then something's wrong. It doesn't make any sense. So the three rules of linear normal regression model, the statistical model, can be expressed all here with this variance term. All right, so let's write out the variance term. So the variance, which we have in here, which is equal to sigma squared I, we can write in the most general framework in this way. So this is the variance matrix unconstrained. This is a heteroscedastic regression model, which I will take this and eventually make. But I'm going to start from the most unconstrained model, because the linear regression model has this specification, and that's an assumption, but we want to understand it. So for starters, this could be the pattern. There could be the pattern across the variance covariance matrix with n rows and n columns, all have different values, and is not diagonal with constant values on the diagonal. The covariances are not zero. The diagonal elements are not necessarily the same. In linear regression, we set the covariances to 0, so I just did that. You can see there 0. We're going to assume independence. If we assume independence, we get one step closer to the linear normal regression model by setting those covariances to 0. Okay, so now what do we do? Now let's notice that this still allows for heteroscedasticity. Heteroscedasticity means a variance that varies. So these numbers are not the same across all the observations. There's n of these, n observations, and the variance of each of these in the regression are all the same, but here they vary. So what do? Well, we now assume, in addition to independence, which are the off-diagonal 0 elements, now we're going to assume homoscedasticity, which are the on-diagonal elements, which we're now assuming are the same. We can rephrase this thing by having 1s on the diagonal, and we can bring sigma squared out front. And now we recognize that that big matrix is just an identity matrix, and we can write the whole thing as sigma squared I. So this is the standard linear normal model regression assumptions. Okay, so what if those assumptions are wrong? What if that big variance matrix is not equal to sigma squared I, and we run the regression anyway? Well, the coefficients are unbiased. The coefficients are B in linear regression framework. We can get the maximum likelihood estimate by deriving the analytic formula for the maximum likelihood estimate, and it is equal to the least square solution. X prime X inverse, this is Q, which is X prime, so X prime X inverse, X prime Y. And it's unbiased. How do we know it's unbiased? We can prove it's unbiased. The expected value of B is the expected value of the formula for B. And now by the expected value of linear functions, when we have a constant term, and X is constant in the linear regression expression, they come out of the expectation. So Q, which is X prime X, and X prime all come out of the expectation. We have the expected value of Y. What's the expected value of Y? Well, we know that from the systematic component. The expected value of Y is X beta, so we plug that in. Now we notice that X prime X is Q, and Q inverse times Q goes away, and this thing is beta. So now we've just proven that the expected value of B is equal to beta, therefore it's unbiased. So that's our proof of unbiasedness. The true variance of B is the following. We'll also calculate this. It's the variance of the formula. In the rule for the variance of linear functions, we can take the constant, which is x, and also q inverse, take it out, but you have to square it. How do you square something in matrices? Well, you take it out at the beginning, and you take it out at the end with a prime. And so that's what that is, right? So we have the q inverse x prime taken out at the beginning, and we have q inverse x prime at the end, and the way you transpose it is it's x prime, which is just x, q inverse prime, which is just q inverse, okay? And if you look at that, then we can write that thing as, but once we substitute in for sigma square, for the variance of y, which we know is sigma, so we'll just put sigma there, and that's what that is. Okay, now, this thing is not equal to sigma squared q inverse, which is the usual matrix, the usual expression for the variance that we have, the diagonal of which are the standard errors. So the usual estimate of the variance of B, of the variance covariance matrix, is biased unless the variance of Y is equal to sigma squared I. So what's the consequence of this? Well, all the simulations from the model are wrong. So most of the quantities of interest we would calculate are biased. We would not want to use this. That means, just to say it again, that the variance part of the model is essential to most of the quantities of interest. It's not essential to the mean because to the coefficients themselves, because we've proven that the coefficients themselves are unbiased. But other quantities, like the probability that a candidate's going to get a majority of the vote, are biased. The variance of the predictions, they are biased. So some quantities are biased, some quantities are not biased if you mess up the variance covariance matrix. What we might do is, instead of having this, we do have the variance of the b's. So this is the variance of b, which is equal to this. Why don't we just estimate this whole thing? We already know q inverse, it's x prime x, and we have x. We know x prime, we know x, and we know a q inverse. All we need to know is sigma. So why don't we just use sigma? We can't use sigma because we don't know it. And we can't estimate sigma because it's an n by n matrix, and even though it's symmetric, there's a lot of elements in there. We'll never be able to estimate them all well anyway with only n observations. It doesn't make any sense that we could estimate more than n things with n observations, so it seems hopeless. And actually for decades and decades and decades, it just seemed hopeless until Hal White and some others realized that we don't actually need all those parameters. We need fewer parameters than it seems. So here's this same expression written down here, but with all the dimensions, just so we can get a feel for it. This matrix itself, sigma, is an n by n matrix. It's way too huge. But if you look closely at this thing, x prime sigma x, that's only a k by k matrix. So that has way fewer parameters. And if we think of that, which I'm going to call G, as a matrix to estimate, it's conceivable, because K is just the number of variables, number of explanatory variables, it's conceivable then that we could estimate G with n observations. And that's the idea, because K is much less than n. So this is a really cool idea, really surprising idea. It means we can estimate the variance of B even when there's heteroscedasticity. And the way we do it, it turns out there's an easy way. So you take the big n by n variance covariance matrix sigma. We're still going to assume zero, we're going to assume independence, so we'll have zero covariances. And we replace the sigmas on the off-diagonal elements with the residuals from a first run of regression squared. And you square them because they're an estimate of the variance. They're not a good estimate of the variance individually, but we don't actually care about them. We only care about their contribution here. So that's exactly what we're going to do. We then put those on the diagonal element here. We calculate this whole thing, and we get a different estimate of the variance of B. They're called robust standard errors, or this is a robust variance covariance matrix, the square root of the diagonal of which are the robust standard errors. This specific case which I've shown you for pretty clear matrix algebra in the linear normal regression model, will generalize to all kinds of different maximum likelihood models. And it's been proven that there is the equivalent of this for pretty much any maximum likelihood model. Let's go over here. The proof is, when you do it this way, that even when there's heteroscedasticity, robust standard errors will give you statistically consistent estimates. So that's great, estimates of the standard errors, that is. But the model itself may still be wrong. And if the model is wrong, the simulations are not right. And many quantities of interest will still be incorrectly estimated, will be estimated in a biased way from this model. So you want to be very careful from this. It's really cool, it's really useful, but only for this purpose. So for robust estimators to help, just to give you a feel for this, everything has to be just right, just right. So we're going to give you a rock, and we're going to give you a hard place. So if the model's misspecified, you're on one side, you don't want to be there. The point estimates of any relevant quantity of interest could be biased. On the other side, the model's correct. And if the model's correct, your point estimates are correct, everything's great. The problem is that when can robust standard errors help? They can help when you're in the middle, when the model's not too misspecified and when it's not correct, right? When it's wrong, but it's not too wrong. When it's in the Goldilocks region, right? When it's just right. And who's in the Goldilocks region? Our goat is in the Goldilocks region. You see this guy? He's stuck in there. But right in there, if he's right in there, he can't go too far. If the model is too misspecified, everything's wrong, including the standard errors. If it's correct, well, there's no point in using it to begin with. So you really have to understand that robust standard errors absolutely can help, but only in this region, and you need to know whether you're in this region. Okay, so they're biased just enough to make robust standard errors useful, but not so biased as to make everything else useless. Okay, the Goldilocks region is not an idyllic, wonderful place to be. You don't want to be that goat. Only a few quantities of interest can be estimated. For example, if Y is the democratic proportion of the two-party vote, you can estimate beta and you can get an unbiased estimate of it. But you can't estimate the probability that the Democrat wins because it uses features of the stochastic component of the predictive distribution that robust standard errors are not going to fix. You can't estimate the variance in the vote outcome. You can't estimate vote predictions with appropriate confidence intervals. We don't know the substantive meaning of our results then. So that's really it's really a problem. How big are they really? You really need to know these things. We can't check whether the model implications are realistic because there are a lot of observable implications of the model that indicate the model is wrong, right? And so if you're going to use robust standard errors in that region, you got to really know that that's the thing that you care about. Parts of the model are wrong. Why do we think the rest is right? It's a particularly optimistic viewpoint that when you look at one observable implication, the heteroscedasticity, homoscedasticity assumption, and you find that it's wrong, why do you think the rest of the model is right? Okay, it could be right, it might be right, but if one thing's wrong, why assume that the rest is wrong? It's much better to assume that the rest is probably wrong too. Let's see whether we could correct it or at least check for it or at least verify that the rest is right. So if classical standard errors and the robust standard errors give different answers, we should hunt down the misspecification in the model. We should find what was wrong originally with the model, and then fix the model, and then rerun the model until the standard errors, the classical standard errors, and the robust standard errors coincide. Because when they coincide, then you have this test for model misspecification that you passed, which is a much better situation than just trying to slap together a fix for one part of the model. If your boat's leaking, yeah, plug the hole, but look around to see if there's any other holes. Okay. So let me now give you an application of this to give you a feel for it. Because what Molly and I did in our paper was was we replicated a number of existing papers, and we showed that the robust standard errors indicated that they were very different from the classical standard errors. And so it didn't necessarily change the conclusions of the article, but in all cases when those two differ, it indicates something's wrong with the model. So we hunted down the features of the model that were wrong. We corrected for those features, and then we looked for other interesting things that we could learn once those features were corrected. So this is a really interesting paper in International Studies Quarterly, published in 2003. The claim of this paper is the flow of multilateral aid are biased towards in favor of smaller, less populous countries. And the method in this paper chosen by Neumeier, the author of the paper, was linear regression of multilateral aid flows regressed on log population, squared log population, and a bunch of control variables. And the result was there was a coefficient on log population of minus 3.13. Now, normally, I would not encourage you to focus on that coefficient because I'm not even going to give you a substantive interpretation of it. But I don't want to change and go to a better way of calculating quantity of interest. I want to just focus right on what was done in the paper so we can fix just that one thing, and we'll be able to focus on the methods here. When you want to focus on substance, which is what you should normally be doing, go all the way to the quantity of interest, of course. Okay, so we replicated the model, and we showed that the robust standard errors were actually twice the size of the classical standard errors. That's big, okay? So for this coefficient, this is the classical standard error, but the robust standard error was really a lot bigger. Okay, so that doesn't indicate necessarily a change in the, let's say, the significance of this coefficient because it's still, more than twice the standard error, but it does very clearly indicate that there's something wrong with the model. So it is clear indication of misspecification. So we went out and to look for the misspecification. What we found was that the outcome variable was very skewed in a particular way, even after we took into account the explanatory variables. And fixing that really helped a lot. So fixing it by taking a log would help, but we found another transformation called the Box-Cox transformation, which is very much like a log. In fact, a special case of it is a log, it just has an adjustable parameter. The Box-Cox transformation was authored by two guys, one named Box and one named Cox, and they decided to write a paper together because they thought it would sound good. And both of them were really good statisticians, and so they came up with a really great idea. So we took the Box-Cox transformation of the outcome variable, just think of it as a log for now, reran the whole model, and now the robust standard error is approximately the same size as the classical standard error. So now we have an indication that there is no longer model misspecification. Of course, there may be some other model misspecification. You can't test all of it, but at least this one seems to have gone away. So that means the original specification was the non-normality there probably was the problem. So now we have no evidence of misspecification. The Box-Cox transformation makes y look normal. Let's just look at y. So here's the distribution of y. It's very heavily skewed with an observation here and an observation all the way out here. After you take this Box-Cox transformation, it now looks much closer to normal. But now pause just for a second. Is this a good test of normality? I gave you a quiz like that a bunch of presentations before. It's not a good test of normality because the normality assumption is conditional upon x. And I'm not conditioning on x here. I'm just showing you the dependent variable. Okay, so why the heck did I do this? Well, because it's closer to the actual variable, it's multilateral aid flows, and the explanatory variables don't actually explain a lot in this model. And if I showed you the distributions of the residuals, it would look very similar to this. Not exactly the same. That would be a better way. That's conditional upon the x's that could cause apparently non-normality. So that is the actual way that we tested it. But I just thought this would be a clearer picture. Okay, so transformation of y not only removes the non-normality, it removes a quite remarkable kind of heteroscedasticity. So here are the actual residuals. Remember, this is the better way of doing it. Here's a key variable in the analysis, log population. Now note what's going on here. So 0 means no error, and the error from 0, either up or down on this axis, is very small for log population small, but very large when log population is large. This is textbook heteroscedasticity. It basically goes up like that and down like that, right? So it fans out. You can see it, when you see it fanning out, the variance is very large on the right and very small on the left. That is, if you were going to write a textbook on heteroscedasticity and use heteroscedasticity in the textbook, come back to this example. It's really great. After we alter the model with this Box-Cox transformation, now we have log population here, and we have residuals here, and the vertical variance, remember here's the 0, right, the 0 line. The vertical variance around the 0 is about the same regardless of what log population is. Maybe it gets a little smaller out here, although the n is smaller out here. So it's pretty much the same all along. In any event, it's way better than it is over here. So that's another correction that this one change made to the model. These are all the graphs. We also looked at a QQ plot, which is a better test of normality. Here is the author's original model. Here's the altered model. The altered model shows that the theoretical quantiles is much closer to the standardized residuals, which is what you want with a QQ plot if you want to have a look at it. Okay, last slide. I want to give you some results, which actually completely changes the substantive results in an interesting case. The author's model shows that log population, well, let's see, the horizontal axis here is log population. The vertical axis is the expected aid that you would get as a percentage of GDP. So what the author showed in the author's model is that this aid drops as log population increases. So for when log population is small, there's more aid. When log population is large, there's more aid. There's a lot of variance in this model as estimated by the model. When we ran the altered model, the model with the Box-Cox transformation, we find that the result is exactly the opposite. Instead of aid going down in population size, it actually goes up in population size, which we think actually makes more sense if it's a bigger country. If there's more people, we might give more, the US might give more money to it, or other countries might give more money to it. So correcting for misspecification sometimes leads to dramatically different substantive conclusions. You absolutely want to pay attention to that. So here's a little quiz. Why are the confidence intervals smaller for the correctly specified model? Well, these are not the confidence intervals here. They're the confidence intervals estimated from the model. Why are the estimates here so large and the estimates here are small? Why is that? Do you know? So the reason why is because in this model, they were these really big outliers. And the outliers, the model is straining to fit. And when it finally fits, what it does is it just increases its confidence intervals to try to encompass the misspecification. So it was good that it had these large confidence intervals. In fact, they weren't quite large enough. But once we fit the model well, it turned out there weren't any big outliers, and it just did quite a good job. So once you correct for model misspecification, you can really get very different results. Okay, so that's robust standard errors. Robust standard errors are just one technique to look for model misspecification. There's lots of other techniques. This technique is very commonly used. For the most part, it's used because people think it's going to inoculate themselves from criticism from reviewers. That's not what it's used for. What it should be used for is for a test of model misspecification. So just go out, sure, run your model, then run robust standard errors, see whether they're different. If they're different, then that indicates that you should probably change something about your model. If you're analyzing somebody else's data, this is a great thing to do. It's a really quick way to get a sense of whether the model is misspecified. It's not any test of model misspecification. It doesn't verify that the entire model's right, but it gives you a pretty good sense that at least some features of the model might or might not be rejected. If they are, you can probably find what was wrong. When we found the Box-Cox transformation, it wasn't like the first thing we thought was, hey, let's try the Box-Cox transformation. We tried plotting all kinds of different things and looking for problems until we settled upon the distribution of the outcome variable that we think was confused, and so it was mistaken. And so we tried the log, and that didn't quite fit very well, and then we looked for and found the Box-Cox transformation, and that fit well. Okay, so thanks for listening. See you next time.